All right, guys, welcome to lesson 4.5. We are kind of shifting a little bit back to learning about some basic operations with matrices. Today we're going to learn about things called determinants and inverses, and we're going to learn about these so that we can continue to apply matrices to other things like systems of equations and solving equations. So let's jump right in. Some key terms you need to know are square matrix, and this is just a matrix with the same number of columns and rows. It's exactly what it sounds like. Something like this that has 2 rows, 2 columns. It makes a square. The multiplicative identity inverse is a square matrix, and it has ones along the main diagonal. So the main diagonal is the one that goes from the top left corner to the bottom right. And so the square matrix would look like this. It would have ones along the main diagonal and it would have zeros everywhere else. So something like this would be an example of a multiplicative identity matrix. Multiplicative is just a fun word to say. Multiplicative inverse is if 2 square matrices, when we multiply them together, we get the product of 1. And you'll see what that looks like here in a few minutes. All right. So first we're going to show that R is the multiplicative inverse of Q. So we are going to take these two and multiply them together. Remember, multiplicative inverse means that we multiply them together and get a product of 1. So I'm going to do RQ, and we get -8, 3, 5, -2, -2, -3, -5, -8. Now, when I multiply these together, I'm using first row and first column. That's going to give me 16 minus 15. Over here, it's going to give me 40 minus 40. Down here, I'm going to get -6 plus 6. And here, I'm going to get -15 plus 16. That is a really bad 16. Let me fix that. There we go. All right, so simplifying a little further, I would get 1, 0, 0, 1. And so it's not just getting the answer of 1, it's actually saying that it's going to be the multiplicative identity matrix. And so we have ones on the main diagonal, zeros elsewhere, so that means that, yes, they are multiplicative inverses. All right, so we are going to look now at determinants, and determinants are going to help us find inverses, and we'll talk again a little bit about what inverses are and why we need them here in a few minutes. But to find the determinant of a 2 by 2 matrix, we take the first diagonal and multiply these two numbers together, and then this is important, we subtract. That's different from when we're multiplying matrices where we add the numbers together. So we have to subtract the other diagonal. So it's just the first diagonal multiplied minus the second diagonal multiplied. And we write the determinant a couple of different ways. We can either write it as the DET of capital A. Remember, we use capital letters to show that it's a matrix. We can also write it as, it looks very similar to a matrix, but instead of having the square brackets, it's missing these little pieces on the top and bottom. It's just straight lines. It almost looks like taking the absolute value of an entire matrix. That's not what we're doing, but that's kind of the symbol that we can use. All right, so find the determinant of the matrix. So I'm going to write this like that, and I'm going to say, all right, first thing, I'm going to take the first diagonal, or the main diagonal, and multiply those together. 8 times 3. And order matters, so be careful. And then I'm going to minus, let's do blue, the other diagonal, 2 times 7. When I do this, I'm going to get 8 times 3 is 24, and 24 minus 14 is 10. And that's it. That's our determinant. Find the determinant of this matrix. So try this one on your own and then see what you get. All right, hopefully you got 1 because what I'm going to do is take the first two numbers, multiply them together, and that gives me 16 minus the second diagonal, or the opposite diagonal, multiplied together is 15. So when I subtract those, I get 1. So that's finding the determinant. But why do we need a determinant? We're going to use a determinant to find inverses. And so I said before that we don't divide by matrices, but multiplying by the inverse is the same as dividing. So there are going to be times when we need to divide by a matrix, and that's the same as multiplying by the inverse. So remember, we talked about like 3, the inverse is 1/3. If I multiply those together, I end up with 1. So even though I'm technically dividing by 3, I'm writing it as times the inverse. So I'm going to find the inverse of a matrix in order to divide by it. So if we have a matrix where the determinant is 0, then A has no inverse. So if A is 0, A has no inverse. But if the determinant of A is anything other than 0, a positive or a negative, decimal, whole number, doesn't matter, then this is the formula that we're going to use to find the inverse matrix. We're going to do 1 over the determinant, and then we're going to take this right here, and we're going to switch the order of the main diagonal, just flip-flop those two numbers. And on the other diagonal, leave them where they are, but change their signs. We're going to practice with this. So we are going to determine whether the matrix has an inverse. So let's start with that. To determine if it has an inverse, we have to test the determinant. So the determinant is going to be 2 times 3 minus 1 times 4. That's going to give us 6 minus 4, which is 2. 2 is not 0, so that means yes, it has an inverse. It only does not have an inverse if it's 0, if the determinant is 0. So if the inverse exists, find it. So I put our little formula up here as a reminder that we are going to need the determinant, and we're going to do 1 over our determinant, which was 2. And then I'm going to multiply this by switching the order of these two. I'm going to put 3 and 2. On the other diagonal, the numbers stay where they are, but I change their sign. So I'm going to get -1 and -4. And now it's just scalar multiplication. I'm going to multiply everything in that matrix by 1/2. And I get 3/2, -2, -1/2, and 1. This would be my inverse matrix. Let's try one more. We are going to solve for matrix X. Now, I said we can't divide, but remember we said that dividing is the same as multiplying by the inverse. So I'm going to find the inverse of this matrix right here, because if I can find the inverse, I can move it to the other side. So to find the inverse, I'm going to do the determinant first, and it's going to be 7 times 2. You do not have to show this part every time. You can just go ahead and write 14. I'm showing it so that we make sure we know where we're getting all these numbers from. That's going to give me a -1. Again, my determinant is not 0, so I'm okay. So to find the inverse, I'll just call this matrix A. I'm going to do 1 over the determinant, and I'm going to switch the order of the numbers on the main diagonal. And then I'm going to leave these numbers where they are, but change their sign. And now I'm going to go through and multiply everything by 1 over -1, which is really just changing the sign of everything. So the inverse is going to be, -2, 3, 5, -7. All right. I could show my work of multiplying this inverse matrix by this matrix and show that they would make the equal to 1. They'd be multiplicative inverses, but that's just what I spent all this time doing, so I'm not going to show that work. Instead, what I'm going to do is I'm going to multiply this side over here by our matrix. And the order matters again, because remember, to multiply them together, we'd have to say, we've got a 2 by 1 and a 2 by 2. So does this work? No. It doesn't work because these inner numbers are not the same, so I have to put the multiplicative inverse in front of that. So I'm going to rewrite the -9, -4 matrix over here. And when I multiply these, I'm going to get x equals, and I'm going to get -2 times -9, oops, sorry, -2 times -9 is +18, plus 5 times -4, which is -20. So I'm going to get -2. Then I'm going to get 3 times -9 is -27, plus 28, which is going to be +1. If I wanted to check my work, I could plug this in back for x and check that the 7532 times -21 is equal to -9, -4, but this would be my final answer. Let's actually go ahead and do one more of those. So if I wanted to solve for x here, the first thing I need is the inverse matrix. So I need the determinant. I'm going to get -15 minus -16. Well, two negatives make a positive, so it's -15 plus 16, and that would be 1. So since my determinant is 1, the inverse does exist because it's not, the determinant's not 0. And to get the inverse, I'm going to do 1 over my determinant times, on that main diagonal, I'm switching the numbers. So I'm putting -5 here and 3 here, and then changing the signs here, -4 and +4. Since my determinant was 1, I can just say it's actually going to be the same, because if I multiply everything by 1, it stays the same. Now I can take this and multiply it, but remember, the order matters. So you can either think of it as I'm putting this in front of the matrix, or you can think of it as I'm going to just bring this down here. That's usually what I do, but I wanted to show you on the last slide that it doesn't work to put it after. So we put 0, 0, -22, -28. Here we go. Okay. So when I multiply these together, I get -5. I'm doing the first row times the first column, and I get 0 times 0. So that's easy. That's just 0. -5 times -22 is +110, plus 4 times -28, which is -112. Had to do some math there in my head. And then -4 times 0 is 0, plus 3 times 0 is 0. And then I've got -88 plus negative, or so minus, 84. All right, so, oh, that should be a +88, sorry. So when I simplify that a little further, I get 0, 0, and then I get -2, 2. And this would be our final answer for x. So like I said, we're going to need inverses and determinants and all that as we go to make sure that we have a good understanding. It's kind of like learning how to multiply so that you can go on and do other things. We're going to apply this a little bit more later in the week, but if you have any questions in the meantime about how to do this, please, as always, let me know.